So, hi guys, I'm Arthur. It's first time presenting a very specific topic in machine learning. So, for this workshop or reading group, we'll be talking about how to improve neural networks performance and take another approach and look at neural networks and to see if there's anything we can do to modify the structures and things like that. And intending audiences would be anyone who knows what a neural network is. And no worries, we'll take a recap on neural networks. So neural networks was inspired by biological neurons and works like a circuit, but unlike a circuit, it's pretty slow to train it and to do inference on it. And it contains an enormous amount of parameters within the entire network. And here below is a very simple 3-layer, actually 5-layer neural network with input and hidden layers and output layer. And if we look at the picture on the right, it depicts how the single neuron works. So we have 3 inputs. Actually, one is the bias neuron, so we can ignore it for now. And we take x1, x2, feed into the functions. And after an activations functions, you can choose 4 or choose, you can choose one from the left. And there are actually much more activation functions besides this. And after that, you get y. And that's basically how the single neuron work. And if we look at a simple class of neural network or layer called feed-forward, or sometimes called dense in the academia. So here's a 3-layered simple network with 1 input layer, 1 hidden layer, or 1 dense layer, and 1 output layer. So we can treat bias as just numerical values like 1 and take them into calculations. So the output will be just simply input times the weight or the parameters of the or the parameters theta and plus a bias unit neuron. And if we look at this in linear algebra, that will be y hat is equal to x times theta, which is the weight transpose, plus b, the bias, and you'll have your output. And we do an activation on this. So if we take a closer look at this simple neural network, we will see, it's pretty robust since you have very intricate connections between each layers, and thus that does the feature engineering or feature selections for us, and it will be able to learn very complex patterns, and it looks cool, of course. However, there are many disadvantages with this. Sometimes a state-of-the-art neural network will take weeks or months to train. And it is very hard to design the architecture. As you can see, all the architectures nowadays, you can see, are pretty much hand-tuned and hand-designed. And during training, there are many uncontrollable variables, such as the hyperparameters and things like that. And today we'll be talking about sparsity techniques. So for a neural network like this, or even larger, will be mostly consist of useless parameters. Yeah, so I can see a question from Aiden. Hyperparameters are a weight of weights and biases. Actually, parameters are matrices of weights and biases. Hyperparameters is something like, for example, during optimization, you have to choose like a learning rate, or even for each layer, you can control the number of input neurons and the number of output neurons. So they are hyperparameters. Okay, I'll move on to the next slide. And if you look at the growth trend for neural networks, especially for large language models, it's growing exponentially, and it seems to be a new Moore's law. And as you can see, Megatron Turing analogy is pretty huge, around 530 billion parameters for a single neural network. And if we take a look at previous state-of-the-art, basically CV-based or computer vision-based architecture named AlexNet, and you can see, take a picture of 227 by 227, and 3 is the number of channels, RGB basically, and pass into the network. And if you look at the network design, it consists of many parameters. For example, each first layer consists of 55 by 55 by 96, and that's huge. And for later layers, it's basically divided by 2 in terms of width and height, and just adding up the channel length. So if you look at the design, you can find patterns within the. So the channel is growing, the number of channels is growing, and the width and heights are basically reducing. And finally, you pass it into a fully connected neural network, like a dense layer, and get your results out of it. It's pretty simple, but consists of a lot of parameters and hyperparameters. And so that's AlexNet, the winner of 2012's image classification challenge. And if we take a look at a larger model named VGG19, it was pretty popular. And if you look at the architecture design, you can find patterns pretty much the same as AlexNet, just stacking up many layers of convolutional layers and reducing the width and height by 2, and just keep increasing the number of channels. And so it got me thinking, so just to get a better performance, we just stack as many layers of convolutional layers as we want. And if we look at this diagram, it's actually not that. So the area or the size of the circle of each circle represents number of parameters it has. So you can see VGG19 is pretty huge, but look at the top one accuracy of the ImageNet image classification challenge. It is not the highest. And if you look at ResNet 15 or even ResNet 18, it's pretty small, but has a very decent accuracy. And if you take a look at neural networks again, you'll find there are many ways we can optimize it, because as I said before, neural networks consist of mostly useless parameters. So there are many ways to reduce parameters by maintaining a very high accuracy. For example, we'll talk about low rank approximations, basically singular value decomposition as the math fundamentals of it, and quantization. And they're very easy to understand. So for low rank approximations, As I said previously, we have a weight matrix theta for in this case, and there are actually two thetas. So theta 1 would be the connection of the first layer, input layer, to the second layer, which is the hidden layer. And the second matrix, theta 2, would be the connection or the weight matrix of the second layer to the third layer. So basically, two matrices for this case. So let's take a matrix A, but let's denote this as theta. We can approximate it using U times V. So using the singular value decomposition, so like a linear algebra trick to decompose our matrix A or theta into three matrices, and basically take the matrix U and find the number of rows that has that contains the most variance, and truncate it, and we got a truncated version of U. So top K, we take the top K rows of actually columns of matrix U, and find V. In this case, we have V transpose, and multiply them to approximate A, and thus reducing a lot of parameters. In terms of quantization, it is very easy to understand. So let's look at a signal. Let's see this sort of sine curve, and we approximate it using the red line. So if you look at the picture on the right, we have a matrix, 3x3 matrix, and consists of 32 floating points, and we want to quantize it to int 8. And it is very easy to achieve this. So for floating point 32, it consists of, let me see. It consists of mostly useless information because it is very precise. And for a smaller network, we don't need that precision. So we can do quantization on it. So let's see how to do that. For example, we have input X. We just basically scale the matrix. So this matrix, the FP32 matrix, scale them into range of 0 to 1. And then we transform it to a new domain. So it's basically the new x tilde would be 2 to the power of number of bits. So let's see, 4 to 2 to the power of 4 multiplied by x prime, and that'll be your numbers in the new domain. And that saves off space, since different types of numbers consumes different cache or different size of memory. And what if we just remove neurons from the architecture? Can we do that? Or we can just remove some useless connections, or just randomly remove some connections to maintain similar performance. And even our brain does so why not? So less than 10% of a human's brain is basically very active during all the time, and the remaining 90% or even more are not being very active by any time. So what if we can just learn from this phenomenon to apply it to our neural networks to make the activation functions more efficient, to make the whole training process flow easier. And that's from the paper from Yan Lekun. He said by removing some unimportant weights or neurons from a network, we can make a lot of improvements. For example, better generalizations, so better accuracy on the test set, and even with some fewer training examples. And most important, speed. So if you look at sparsification techniques depicted in this picture, you can see on the left is a traditional neural network, and after pruning, it looks like the one on the right. So pruning those connections. And actually there are two ways to do so. So the one on the right actually prunes not only the connection, but also neurons. So what is sparse? So what is sparsity? There are mainly two types of matrices. One is dense and one is sparse. If we look at the one on the right, it's basically a matrix with mostly 0 entries. And multiplying a matrix by a matrix of mostly zeros would be very computational efficient, since multiplying by 0 is basically very fast and very easy to do so. So we will want our weight matrix to be sparse, so mostly zeros. And if you look at the weight distributions, the histogram of each layer of a network, we can see, if you look at the activations, the weights of each layer, it looks pretty Gaussian, but actually not. Like, it tends to be Gaussian, but actually it is not. For some layers, such as the first convolution layer is mostly zeros, and this applies to most networks, not only this one, MobileNet V1. So that means if we truncate most zeros, we can greatly reduce the size of the network. And there are two types of pruning strategy. One is structure pruning. So as I said before, removing neurons, because each neuron represents a role in the weight matrix theta. And unstructured pruning is basically removing some entries in a weight matrix. So like this one, you can see it's not removing an entire role, it's removing some entries within the dense matrix. And structure pruning, it is very easy to do so, because you're just removing a role, and you do need to worry about other things, such as how to make it faster when it is multiplying by zeros. And also it is very easy to implement. For unstructured pruning, that is the mainstream people are using nowadays, because basically it has a better performance and has a lot of flexibility, and it is very I would say very complicated to implement. It is very easy to implement on the software side, but hard to implement on the hardware side, because you have to figure out how to ignore multiplying by 0. And that is for the introduction section. And thanks for staying. I wonder if there's any question. Okay. from Aiden. When you say hardware side, what do you mean? Like low level? Yeah. So, for example, you have a matrix like this, sparse matrix, right? Basically the dot entries are basically zeros. So you're doing a matrix multiplication. You have to, for example, for the first row, multiplying this row by this column, and you have to do the computations to add them up. So for example, 31, you have to multiply by 0. And for a normal machine, you have to do that operation. But like for dedicated hardware station, you won't do that. Like you just skip that. So you won't do 31 multiplied by 0. Yeah, it's pretty much low level. It is not for TPU hardware. It is for some dedicated hardware that are specifically that are particular good at doing those sparse operation. So traditional CPU is pretty slow to compute it. It is even slower than the GPU. And imagine if you can save up, all the multiplying by 0 operations, that can speeds it up significantly because you're basically consist of mostly zero entries. And for the coming up section, I'm thinking about taking a more interesting approach to this problem. So we'll be looking at how to improve the training procedures to make the training faster, but with higher accuracy. And it is very interesting that for some, for example, for a network like VGG, we talked about before, like this one. So you find a sub network inside this huge, gigantic architecture, and that sub network with random initialization, so you don't train it at all, can achieve similar accuracy. So that is very interesting because you don't even need to train the subnetwork within it. And generally speaking, sparse network, so networks with mostly sparse entries, are going to outperform traditional dense network like that. And also it generalizes well on the validation data set because it is less likely to overfit on the data set because it has fewer parameters. Yeah, it's kind of like that. I mean, there are many hardwares are dedicated or designed to do sparse operation with very low energy cost, I would say. For example, there's a company called Cerebras System. Yeah, there's a company called Cerebras System that can speed up everything very fast, and they claim to have 100 times faster training time compared to a traditional cluster of GPUs. And not even if we were to implement this, trying to improve our performance, we can probably choose structured pruning it is very easy to implement. And also, by removing a role, you just reduce the operation with these number of operations with these, because you don't even do the operation. Like, you don't need to skip it. Structured prunings, I think there are many like tutorials, and even some introductory Medium posts that that talk about this topic, with fair examples. And if you're interested, probably I'm thinking about doing a workshop, like how to program this from scratch, something like that. But it will be very easy to implement it by yourself if you know the concept. So yeah, for example, if you want to do structured pruning, just if you don't want to improve the accuracy, just want to improve the training speed, you can just randomly remove neurons. So randomly remove rows of vectors within the dense matrix, and you will find a speed up. Yep, no problem. And I think this session is relatively short because it's just an introductory session, and I'll be talking about the details in the coming up session. And thank you guys, and have a great night. I'll end the recording.